Hello everyone, I am Dr. Sirajul Akfaizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about molecular modeling. So, the drug discovery pipeline, we start from here and then we will go to the molecular modeling because molecular modeling is a part of drug action designing. So, drug discovery pipeline, you can see the validating therapeutic targets step by step, target identification and validation, hit identification, lead optimization, CD presentation, concept testing, development for launch, and launch phase. So you can see the target identification and validation, finding potential drug targets. Now finding potential drugs, hit identification, lead identification, and lead optimization. Then CD optimization means drug target therapeutic effect association finalized and testing in man toxicity and efficacy. So drug discovery is a goal of research methods and approaches from different science areas can be applied to achieve the goal. Now you can see the design cycle, lead optimizations. Starting from biological concept, computer-aided design, protein crystallography, NMR, search in 3D database, de novo design. So lead structure, series design, synthesis design, and unique, you can see a structure activity relationship, QSR, molecular modeling, synthesis, biological testing, then candidate for the further drug development, investigation new drugs, IND, and new drug. This is the design cycle. Now, drug discovery, the current status. R&D cost per new drug is like that. You can see this million. To sustain growth, each of top 20 pharma company should produce more new drugs. Currently, total industries produces only 32 new drugs per year. Current rate of NDA far below than required for the sustained growth. So, computational tools, that is the theoretical hierarchy. Atomistics and continuum. In atomistic, you have finite and periodic. You have also the quantum mechanical methods and classical methods. Classical method, deterministics and stochastic. And then stochastic is Monte Carlo and deterministic molecular dynamics. So quantum mechanical methods, you can see semi-empirical and ab initio. In ab initio, quantum mechanics, DFT, Hartree-Fock, and quantum mechanics and molecular mechanics. This is the hierarchy of computational tools. So models versus scales. You have the small molecules, drug, atomic scale, protein membrane, nanoscales, microscale cell, and macro scale organism, and classical mechanics, structural mechanics. Now you can see the continuum mechanics, finite elements method, and fluid dynamics. Statistical mechanics like molecular mechanics, molecular dynamics, Brownian dynamics, and stochastic dynamics. Now you have quantum mechanics, density function theory, Hartree-Fock theory, and perturbation theory. So basic modeling strategy. You can see the ligands, you see the receptor. Unknown and known, unknown and unknown in both receptor and ligands. Now homology modeling, unknown. Generate 3D structure, STS, combinatorial chemistry, build the lock and then find the key. Now both are known, molecular modeling, docking, drug receptor interaction. Now ligands are known but receptor known. De novo design, virtual screening, build or find the key that fits the lock. Now ligands known but receptor unknown. Indirect drug design, 2D, 3D QSR and pharmacophore. infer the lock by expecting the key. Now, definition of molecular modeling. Molecular modeling allows scientists to use computer to visualize molecules, means representing molecular structure numerically and simulating their behavior with the equation of quantum and classical physics. To discover new late compounds for drug or to refine existing drugs in silico. So the goal to develop a sufficient accurate model of the system so that physical experiment may not be necessary. Now, the term molecular modeling spanned over the last decade from a tools to visualize three-dimensional structure and to simulate, predict, and analyze the properties and the behavior of the molecules on the atomic level to data mining and platform to organize many compounds and their properties into database and to perform virtual drug screening via 3D database screening for novel drug compounds. This is the literal meaning of molecular modeling. Now you will understand step by step. Now you can see molecular modeling start from structure determination, selection of calculation method in the computational chemistry, starting geometry from standard geometry, X-ray, etc. Then you have the molecules, you have the in your hand quantum mechanics, you have molecular mechanics, you have molecular dynamics or Monte Carlo. So you can see here one side is bond formation or breaking importance. Are many force field parameter missing? Is it smaller than 100 atoms? Are charges or of interest or not? In another side, we have the macromolecules, like are there many closely spaced conformation? Is plenty of computer time available? Is the free energy needed? Is solvation important? So these parameter. Now you can see the model first. Stick, ball and stick, space filling, we call it CPK, and wire frame. This is the molecular modeling of the molecules. Now, computational chemistry approach. You know, molecular modeling or more generally computational chemistry in scientific field of simulation of molecular system. Basically, in computational chemistry, the free energy of the system can be used to assess many interesting aspects of the system. In the drug design, the free energy may be used to assess whether a modification to a drug increase or decrease target hiding. The energy of the system is a function of the per type and number of atoms and their position. You know, molecular modeling software are designed to calculate this efficiently. The energy of molecules play important role in the computational chemistry. If the algorithm can estimate the energy of the system, then many important properties may be derived from it. You know, on today's computer, however, energy calculation takes days or months even for a simple system. So in practice, various approximation must be introduced that reduce the calculation time while adding acceptably a small effect on the results. So need of molecular modeling. So familiar conformation of the butane. You know the conformation of butane because here is the dihedral angles. So molecular modeling are two types, quantum mechanics and molecular mechanics. Ab initio methods and DFT, density function theory method, and semi-empirical methods. So what is quantum mechanics? Quantum mechanics is basically the molecular orbital calculation and offer the most detailed description of molecular chemistry behavior, like HOMO, highest energy occupied molecular orbital, and LUMO, lowest unoccupied molecular orbital. So quantum method utilize the principles of particles physics to examine a structure as a function of electrons distribution. You know, geometries and properties for transition state and excited state can only be calculated with the quantum mechanics. You also know their use can be extended to the analysis of molecules as yet unsynthesized and chemical species which are difficult or impossible to isolate. So, quantum mechanics is based on Schrodinger equation Si is equal to E psi is equal to U plus K psi. You know the E energy of the system relative to one in which all atom particles are separated to infinite distance. H Hamiltonian for the system, it is an operator, a mathematical construct that operate on molecular orbital psi to determine the energy. U potential energy, K kinetic energy, psi wave function describe the electron distribution around the molecules. So the Hamiltonian operator H in general, you can see H particles and particles like and all parameter like quantum mechanics. So you can see where Vi square is the Laplacian operator acting on particles I. Particles are both electrons and nuclei. The symbols Mi and Qi are the mass and charge of particles I, and Rij is the distance between the particles. Now, the first term gives the kinetic energy of particles within a wave formulation, and second term is the energy due to Coulombic attraction or repulsion of particles. So, Born-Oppenheimer approximation, what is that? In currently available software, the Hamiltonian above is never used. So the problem can be simplified by separating the nuclear and electron motion. So you can see the kinetic energy of electrons, attraction of electron to nuclei, and repulsion between electrons. So you have three parameters here in three: electrons, nuclei, electrons, and electrons. So each electronic structure calculation is performed for a fixed nuclear configuration, and therefore the position of all atoms must be specified in input file. So have an issue program like MolPro then computes the electronic energy by solving the electronic Schrodinger equation for this fixed nuclear configuration. You know the electronic energy as a function of 3n-6 internal nuclear degree of freedom define the potential energy surface PES, which is in general very complicated and can have many minima and saddle points. You know the minima correlation to equilibrium structure of different isomers or molecules and saddle point to transition state between them. So, ab initio method, the term ab initio in Latin for from the beginning and premises of the quantum theory. This is the approximate quantum mechanical calculation for a function of finding an approximate solution to a different equation. You know, it is purest form quantum theory uses well-known physical constants such as velocity of light, value for the masses and charges of nuclear particles and differential equation to directly calculate the molecular properties and geometries. And this formalism is referred to as ab initio from first principle quantum mechanics. Now, Hartree-Fock approximation, what is that? So the most common type of ab initio calculation in which the primary approximation is the centered field approximation means Coulombic electron-electron repulsion is taken into account by integrating the repulsion term. So this is the variational calculation, meaning that the approximate energy calculated are all equal to a greater than the exact energy. The energies are calculated in unit called Hartree. One Hartree is equal to 27.2116 electron volt. So the step in a Hartree-Fock calculation start with the initial guess for the orbital coefficient, usually using semi-empirical methods. And this function is used to calculate an energy and new set of orbital coefficient, which can then be used to obtain a new set and so on. So these procedures continue interactively until the energy and orbital coefficient remain constant from one interaction to the next. And this interactive process is called as a self-consistent field procedure. So what is the advantage of this? Advantage of this method is that it breaks the many electron Schrodinger equation into many simpler one electron equation. Each one electron equation is solved to yield a single electron's wave function called a orbital and an energy called an orbital energy. So ab initio method, you can see the methods, advantage, disadvantage, best for. So ab initio useful for a broad range of system computationally expensive, small system, and mathematically rigorous, no empirical parameter, does not depend on the experimental data, electronic transitions. You can see the calculate transition state and excited state. You see the system requiring high accuracy for the Ab initio. Now, density function theory. What is density? How something is distributed speed about a given space. Electron density tells us where is the electrons are likely to exist. So allyl cation, you can see density directly proportional to psi star and psi. So what is a functions? The functions depends on the set of variables. Y is equal to function of x. Wave function depends on the electron coordinates. So functional depends on the functions, and which in turn depends on a set of variables. So E is equal to F and function of x. So energy depends on the wave function, which depends on the electron coordinates, like this. So density function theory, the electron density is the square of wave functions and integrated over electron coordinate. You know, the complexity of wave function increases as the number of electron grows up, but the electron density still depends only on three coordinates. So with this theory, the properties of many electron system can be determined by using functional, that is the function of another function, which is this case is the especially depending electron density. So there are difficult in using density function theory to properly describe intermolecular interaction, especially van der Waals forces, dispersion, charge transfer, excitation, transition state, global potential energy surface, and some other strongly correlated system. So, Thomas Fermi model. Density function theory has its conceptual root in the Thomas Fermi model. It is developed by Thomas in Fermi in 1927. And they used a statistical model to approximate the distribution of electron in an atom. So, the mathematical basis postulates that electrons are distributed uniformly in phase space with two electrons in every HQ of the volume. So, for each elements of coordinate space volume dqr, we are fill out the sphere of momentum space up to the Fermi momentum pi. You can see the 4 by 3 pi r cube. This is the volume. So equating the number of electrons in coordinate space to that in the phase space given. So this is the formula. Solving for PAF and substituting into the classical kinetic energy formula then leads directly to the kinetic energy represented as the functional of the electron density. So you can see the CF is equal to 3h square 10 am 3 by 8 by 2 3 like this. So as such, they were able to calculate the energy of an atom using this kinetic energy function combined with the classical expression for the nuclear electrons and electron-electron interaction, which can both also be represented in terms of electron density. You know, the Thomas Fermi equation accurately is limit because the resulting kinetic energy functional is only approximate, and because the method does not attempt or represent the exchange energy of an atom as a conclusion of the Pauli exclusion principle. So, exchange energy function was added by Dirac in 1928 called Thomas Fermi-Dirac model. So, the Thomas Fermi-Dirac theorem remained rather inaccurate for most application. The largest source of error was the presentation of the kinetic energy followed by the error. So, in the exchange energy due to the complete neglect of the electron correlation. Now, Weinberg-Cohen theorems. DFT was originally with the theorem by Weinberg and Cohen. The original HK theorem, HK means H for Weinberg and Cohen theorem, held only for the non-degenerate ground state in the absence of magnetic field. So first HK theorem demonstrates that the ground state properties of many electron systems are uniquely determined by the electron density that depends on only three spatial coordinates. It lays the groundwork for in reducing the many body problem of n electrons with 3n spatial coordinates to only three special coordinates through the use of functional of the electron density. So this theorem can be extended to the time-dependent domain to develop time-dependent density function theory, TDDFT, which can be used to describe excited state. Now friend, the second HK theorem defined energy of function for the system and proves that correct ground state electron density minimizes energy function. So Kohn-Sham theory. Within the framework of Kohn-Sham density, the intercatable many-body problem of interacting electrons in a static external potential is reduced to attractable problems of non-interacting electrons moving in an effective potential. So the effective potential include the external potential and the effect of the Coulomb interactions between the electrons, that is the exchange and correlation interaction. So EDFT, you can see the electron-electron exchange energy, electron-electron Coulombic energy, nuclear electron Coulombic energy, and electronic kinetic energy. You can see here what is the relations. So modeling the latter to interaction between the difficulty with KSDFT. So in this formulation, the electron density is expressed as a linear combination of basis function similar in mathematical form to HF orbital. So Hartree-Fock orbital. A determinant is then formed from this function called Kohn-Sham orbital. And it is the electron density from this determination of orbital, and that is used to compute the energy. So semi-empirical molecular orbital methods. So semi-empirical methods are very fast, applicable to large molecules, and may give qualitative accurate results when applied to the molecules that are similar to the molecules used for the parameterization. So because the semi-empirical quantum chemistry avoid two limitations, namely slow speed and low accuracy of the Hartree-Fock calculation. By omitting the parameterizing certain integrals based on the experimental data such as ionization energy of atom or dipole moment of molecules. So rather than performing a full analysis on all electrons within the molecules, some electrons interactions are ignored. So modern semi-empirical models are based on the neglect of diatomic differential overlap NDDO method, in which the overlap matrix X is replaced by the unit matrix. So this allows one to replace the Hartree-Fock circular equation. You can see with the simpler equation HE0. So existing semi-empirical models differ by the further approximation that are made when evaluating one end and two electron integrals and by parameterization philosophy. So modified neglect of diatomic overlap MNDO by Michael Dewar and Walter Thief. Austin models 1 AM1 by Dewar and co-worker. Parametric methods method 3 MP3 by James Stewart. PDDG PM3 by Williams Johnson and co-worker. MNDO means modified neglect of diatomic overlap by Michael Dewar and Walter Thiel 1977. In the oldest NDDO based model that parameterizes one center two electrons integral based on specific data for isolated atom and evaluate other two electrons integral using the idea of multiple interactions from classical electrostatics. You know, the classical M and DO models use only S and P orbital basis sets, while more recent M and D adds d orbitals that are especially important for the description of hypervalent sulfur species and transition metals. So deficiencies: inability to describe the hydrogen bond due to a strong intermolecular repulsion. MNDO method is characterized by generally poor reliability in predicting heats of formations. For example, highly substituted stereoisomers are predicted to be too unstable compared to the linear isomers due to overestimation of repulsion in a sterically crowded system. So Austin Model 1 AM1 by Michael Devar and co-workers takes a similar approach to MNDO in approximation to electron integrals but uses a modified expression for nuclear core repulsion. The modified expression results in non-physical attractive forces that mimic van der Waals interaction. You know the Austin Model 1 predict the heat of the energy more accurately than the MNDO, and the results of AM1 calculation often are used as a starting point for parameterization of the force field in molecular dynamics simulation and COMFA QSR. So some known limitation to AM1 energy. Predicting rotational barrier to be one-third and actual barrier and predicting five-member ring to be too stable. The predicted heat of formation tend to be inaccurate for the molecules with a large amounts of charge localization. So geometries involved phosphorus are predicted poorly. There are systematic error in alkyl group energy predicting them to be stable. Nitro group are too positive in energy. The peroxide bond is too short by about zero point 0.1 angstrom. Hydrogen bond are predicted to have character strength but often the wrong orientation. So on average, AM1 predict energy and geometry is better than MNDO but not as well as MP3. So parametric method 3 MP3 by James Stewart uses Hamiltonian that uses nearly the same equation as the AM1 Austin methods long within the improved set of parameterizes. So limitations of MP3 parametric methods 3. PM3 tends to predict that barrier to rotation around the carbon nitrogen bond in peptide is too low. So bonds between silicon and the halides atoms are too short, proton affinities are not accurate. Some polycyclic rings are not flat. So the predicted charge on nitrogen is incorrect. Non-bonded distance are too short. So strength. Overall heat of formations are more accurate than with MNDO or AM1. Hypervalent molecules are also predicted more accurately. MP3 also tend to predict incorrect electronic state for the germanium compounds. It tends to predict sp3 nitrogen as always being pyramidals. Hydrogen bonds are too short by about 0 0.1 but angstrom, but the orientation is usually correct. On average, PM3 predicted energy and bond length more accurately than AM1 or MND. So PDDG PM3, the Johnson and co-worker pairwise distance directed Gaussian. Pairwise distance directed Gaussian. Use a functional group specific modification of the core repulsion function. Its modification uh, provides good description of the van der Waals attraction between atoms. PDDG MP3 models very accurate for the estimation of heat of formation because of reparameterization. But some limitations common to NDDO method remain in the PDDG PM3 model. The conformational energy are unreliable. Most activation barrier are significantly overestimated and description of the radical is erratic. So far, only carbon, nitrogen, oxygen, hydrogen, sulfur, phosphorus, silicon, and halogens have been parameterized for PDDG MP3. Now, some freely available computational chemistry programs that include many semi-empirical models are MOPEC 6, MOPEC 7, and WinMOPEC. So, usefulness. Computational modeling of a structure-activity relationship, design of chemical synthesis or process scale-up, development and testing of new methodologies and algorithms, checking for gross errors in experimental thermochemicals data, heat of formation, preliminary optimizations of geometries of unusual molecules, and transition state that cannot be optimized with the molecular mechanics methods. So semi-empirical methods, the semi-empirical method less demanding computationally than ab initio method required uh, ab initio or experimental data for parameter medium-sized system, 100 of atoms. Now, molecular mechanics. You know, the process of finding the minimum of empirical potential energy function is called the molecular mechanics. It's called as the molecular mechanics. The process produces a molecules of idealized geometry. Molecular mechanics is a mathematical formalism which attempt to reproduce the molecular geometry, energies, and other future by adjusting bond length, bond angles, and torsion angle to equilibrium values that are dependent on the hybridization of an atom and its bonding scheme. So molecular mechanics break down pairwise interaction into bonded interaction, internal coordinate, atoms that are connected via 1, 2, 3 bonds, and non-bonded interaction, electrostatic and van der Waals component. So the general form of the force field equation is EP function of x, E bonded and E non-bonded. So bonded interaction, used to better approximate the interaction of the adjacent atom. Calculation in the molecular mechanics is similar to the Newtonian law of classical mechanics and will calculate geometry as a function of static energy. So Hooke's law is applied here. You can see the F is equal to kx, where force on the spring needed to stretch as ideal spring is proportional to its elongation x, and where k is the force constant, a spring constant of the spring. So bonded E bond angles and dihedral angles. For bond term, you can see the half kb b minus b naught square. Angle term half k theta theta minus theta 0. Energy of the dihedral angles k phi 1 minus cos n phi plus delta. So graphical presentation of bonds and non-bonded interactions and the corresponding energy term. You can see the energy of electrostatic interaction, van der Waals interaction, VWD, and then angles. You can see the angle bending, you can bond stretching and dihedral rotations. Everything you have to consider. So non-bonded interaction nearly apply to all pairs of atom. The non-bonded interaction term usually include electrostatic interaction and van der Waals interaction, which are expressed as a Coulombic interaction as well. So Lennard-Jones type potential respectively. All of them are function of the distance between the atom pair. So non-bonded is equal to van der Waals plus electrostatics. So van der Waals formula is like that, Lennard-Jones potential and electrostatic like Coulombic flow. So what is force field? The molecular mechanics energy expressed consists of simple algebraic equation for the energy of the compound. A set of equations with their associated constant which are energy expressed in called force field. So such equations describe the variation aspect of the equation like stretching, bending, torsion, electronic extraction, van der Waals forces and hydrogen bonding. So valence term in the energy expressed with describe a single aspect of molecular shape such a bond, stretch, bond bending and inversions and rotational motion. That is the valence term. Cross term means term in the energy expansion that which describe how one motion of the molecules affect the motion of the another. Stretch bends term which describe the how equilibrium bond length and tend to shift as bond angles are changed. So electrostatic term force field may or may not be include this term Coulombic's law. So some force fields simplify the complexity of calculation by omitting most of the hydrogen atom. So parameter describing the such backbone atom are then modified to describe the behavior of the atom with the attached hydrogen. So thus the Coulomb's calculation uses a CH2 group rather than a sp3 carbon bonded to two hydrogen. So these are called united atom force field or intrinsic hydrogen method. So some popular force field are AMBER, CAM and CFF. So AMBER assisted model building with energy refinement in the name of the both force field and molecular mechanics program. It was parameterized specifically for the protein and nucleic acid, and it uses only 5 bonding and non-bonding term and no other cross term. So CHARM, Harvard University, chemistry at Harvard, molecular mechanics in the name of both force field and program incorporating the force field. And it was originally devised for the protein and nucleic acid, but now it is applied to the range of the biomolecules, molecular dynamics, solvation, crystal packing, vibrational analysis, and quantum mechanics and molecular mechanics study. And it uses the five valence term, and one of them is an electrostatic term. So CFF, the consistent force field. It was developed to yield consistent accuracy of result for the conformation, vibrational aspect, strain energy, and vibration enthalpy of protein. And there are several variations on this consistent valence force field, and Bradley consistent force field, and Legge consistent force field. So these force field use 5 to 6 valence term, one of which is electrostatic, 4 to 6 other are cross term. So molecular mechanics energy minimization. You know the molecular mechanics energy minimization to find a stable low energy conformation by changing the geometry of a structure or identifying a point in the configuration space at which the net force on atom vanishes. In other words, it is to find the coordinate where the first derivation of the potential energy function equals to 0. So such conformation represent one of the many different conformation that molecules might assume at a temperature of 0 Kelvin. So potential energy function is evaluated by certain algorithm or minimize the moves the atom in the molecules to nearest local minima. So steepest descent, conjugate gradient, and Newton's Raphson procedure. So there are three main approaches to find the minimum of functions of many variable infallible. So search method utilize one value of function, show inefficient search algorithm infallible and always find minima like simplex. So gradient method utilize value of functions and its gradient. Currently most popular example the conjugated gradient algorithm. Newton's methods requires value of functions and first and second derivative Hessian matrix and examples BFGS algorithms. So geometry optimization is an interactive procedure for computing the energy of a structure and then making incremental increase change to reduce the energy. So minimization involves two steps. An equation describes the energy of system as a function of its coordinate must be defined and evaluated for a given conformation. The conformation is adjacent to the lower the value of the potential energy. So you see the algorithm for descent series minimization, L local minima and G global minima. So Cartesian space. What is this Cartesian space? A Cartesian presentation of potential energy surface. The picture would like to lots of narrow towards valley of similar depth. And this is because low energy path of the individual arrow are very narrow due to presence of hard bond stretching and angle bending term. The low energy paths correspond only to the rotation of the group or large proportion of the molecules as a result of varying torsional angle. So in the Cartesian space minimizer, walk along the bottom of a narrow winding channel which is frequently a dead end. So internal coordinates. The internal coordinate presentation, the potential energy surface look like a valley surrounded by high mountains. The high peaks correspond to a stretch and bending term and close van der Waals contact while the bottom of the valley represent the torsional angle of freedom. So if you happen to start the mountain top in the internal coordinate space, the minimizer sees the bottom of the valley clearly from the above. So using the internal coordinate, there is a clear separation of variable into the hard one, those whose small changes produce large change in the function's value, and soft one, those who change do not affect the function's value substantially. During the functions optimization in the internal coordinate, the minimizers first minimize the hard variables and in the subsequent interactions clean up the details by optimizing the soft variable. So while in the Cartesian space, all variables are of the same type. So molecular dynamics, the atoms and molecules are in the constant motion, and especially in the case of biological molecules, these moments are conserved and may be essential for biological function. As so much thermodynamics, so such dynamic properties cannot be derived from the harmonic approximation in molecular mechanics because they inherently assume the simulation method around a systematic minimum. So we use molecular dynamic simulation used to compute the dynamics of the molecular system, including the time average, structural and energy properties, structural fluctuation, and conformation transition. So, dynamic of a system may be simplified as the movement of each of its atoms. If the velocities and forces acting on the atom can be quantified, then their moment may be simulated. So, there are two approaches in molecular dynamics for the simulation: stochastic, called Monte Carlo simulations, and based on the exploring the energy surface by randomly probing the geometry of the molecular system. Now, deterministic, called molecular dynamics, it actually simulate the time evolution of the molecular system and provide us with the actual trajectory of the system. So, stochastic approach Monte Carlo simulation based on the exploring the energy surface by randomly probing the geometry of the molecular system. Step: specify the initial coordinate of the atom, generate a new coordinate by the changing the initial coordinate at the random, compute the transition probability, generate the uniform random number R in the range, and otherwise accept the new coordinate and go to step 2. So this is the Metropolis Monte Carlo rigorous canonical sampling produces Boltzmann weighted populations and inform about the equilibrium state easy to implement. So deterministic approach molecular dynamic simulation, the actually time evaluation of the molecular system and the information generated from the simulation method can be used to fully characterize the thermodynamics state of the system. Here the molecular system is studied as a series of snapshots taken at the closed time interval, femtosecond usually. So principle based on the potential energy function, we can find component Fi of the force F acting on atom as this force is the acceleration according to Newton's equation of motion. So by knowing the acceleration, we can calculate the velocity of an atom in the next time step from atom position. Velocity is an acceleration at any momentum in time. So we can calculate atom position and velocity at the next time step. So integrating these infinitesimal step yield the trajectories of the system for any desired time range. So Worlet algorithm, you can see Worlet algorithm uses positions and acceleration at a time t and position for the time t minus delta t to calculate a new position at a time t plus delta t. So advantage: position integration is accurate, single force evaluation per time step, and forward and backward uh, expansion guarantee that the path is reversible. Now, disadvantage: velocity has large error and it hard to scale the temperature kinetic energy of the molecule. So, leapfrog algorithm. This is the nth algorithm. The velocity are first calculated at time t plus half delta t. The velocity leap over the position. And these are used to calculate the position r at time t plus delta t. Then the position leap over the velocities. So advantage: high quality velocity calculation, which is important in the temperature control. The velocities are known accurately at half time steps away from when the position is known accurately. Estimate of the velocity and integral time steps. So procedure: we need an initial set of atom position geometry and atom velocity. The initial position of atom are most often accepted from the prior geometry optimization with the molecular mechanics, and formally such position correspond to the absolute zero temperature. So the velocity are assigned to each atom from the Maxwell distribution for the temperature to 90 degrees Celsius. Random assignment does not allocate correct velocities and system is not thermodynamically equilibrium. To approach the equilibrium run is performed and the total kinetic energy of the system is monitored until it is constant. The velocities are then rescaled to correspond to some higher temperature, that is heating is performed, and the next equilibrium run follow. So the absolute temperature and atom velocity are related through the mean kinetic energy of the system following this formula. By multiplying the velocity by we can effectively heat the system and that accelerate the atom of molecular system. So these cycles are repeated until the desired temperature is achieved, and this point production is run on commence. So molecular dynamics for large molecules or system in which solvent molecules are explicitly and taken into account in a computationally intensive task even for the supercomputer. For such conditions, we have two approximations: periodic boundary condition and stochastic boundary conditions. So you can see the periodic boundary conditions. So here we actually simulating a crystal comprising of boxes with ideally correlated atom moments. So stochastic boundary condition, this is the reaction zone portion of the system which are want to study, reservoir zones portion of the system which inert and uninterested. So molecular mechanics, molecular mechanics computationally cheap, fast and useful with limited computer resolution, does not calculate electronic properties. So conclusions. So molecular dynamics and molecular mechanics are often used together to achieve the target conformer with lowest energy configuration. Visualize the 3D shape of molecule, carry out a complete analysis of all possible conformation and their relative energy, obtain a detailed electronic structure and polarizability with taken account of the solvent molecule, predict the binding energy for docking a small molecule that is drug candidate with a receptor or enzyme target, producing block boosting drug. And nevertheless, molecular modeling, if used with the cautions, can provide very useful information to the chemist and biologist involved in the medicinal research. So this is the references. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.